Hello everyone and thanks for watching Edupedia World videos. I am Manish Agrawal and in today's session of mole concept we'll continue with chemical reactions and we'll go into details about the calculation part of chemical reactions. Alright, so we'll deal with stoichiometric calculations in today's lecture. So first let's try and understand what we understand by the term stoichiometric coefficients. Alright, we have already studied that stoichiometric coefficients are nothing but the numbers on the left hand side. Alright, the numbers on the left hand side of each molecule in your chemical reaction. The numbers which come after balancing of the reaction. Alright, they are nothing but a result of a balanced chemical reaction. So these coefficients actually represents ratios of molecules, that is number of molecules involved in the reaction, or you can say it is a ratio of number of moles, or in case of gases you can also say that it is a ratio of volumes and even ratio of mass. Let's try and understand what this means. Okay, see, you have a reaction here of formation of ammonia. If you look here, you will see that the coefficient of nitrogen is 1. Alright, since nothing is written, it means it is 1. Alright, and here it is 3 and here it is 2. So now you know the stoichiometric coefficients of each molecule in this reaction. Alright, because they are a result of balanced equation, and this equation which has been given to us is already a balanced chemical equation. So what I am saying is that these numbers 1, 3 and 2, alright, these are not just arbitrary numbers. Alright, their significance doesn't end with the balancing. They actually represent ratio of number of molecules taking part in the reaction. In other words, for every one molecule of nitrogen, I need 3 molecules of hydrogen. For a complete reaction, for every one molecule of nitrogen, I need 3 molecules of hydrogen in my container. And together, when they combine and complete the reaction, these molecules will form 2 molecules of ammonia. Alright, in other words, 1 molecule of nitrogen will form 2 molecules of ammonia upon complete reaction, or 3 molecules of hydrogen will form 2 molecules of ammonia on complete reaction. Okay, so this is ratio 1:3:2. Alright, they are not the exact number of molecules which are taking part in the reaction. Right, their ratio. For example, if instead of 1, let's say I decide to take 2 molecules of nitrogen in my container. Okay, instead of 1, if I decide to take 2 molecules of nitrogen in my container, then correspondingly I will need, instead of 3, now I will need 6 molecules of hydrogen for complete reaction. Okay, the ratio has to be maintained. The ratio of number of molecules of nitrogen to number of molecules of hydrogen required for a complete reaction should be always 1:3. Okay, it is actually always 1:3. So if I take 2 molecules of nitrogen, I need 6 molecules of hydrogen, otherwise the reaction won't go to completion. Okay, and 1 molecule of nitrogen form 2 molecules of ammonia. So 2 molecules of nitrogen upon complete reaction will form 4 molecules of ammonia. Alright, so this is what I mean by ratio. Similarly, instead of 2, I can have, say, 3 molecules of nitrogen. Alright, I can have 3 molecules of nitrogen. If I take 3 molecules of nitrogen, now you can make the calculations by yourself. Hydrogen required is in the ratio 1:3, that is, hydrogen required will be 9 molecules of hydrogen. And upon complete reaction, these molecules will form how many molecules of ammonia? These will form 3 multiplied with 2, that is 6 molecules of ammonia. Okay, So when I am talking about number of molecules, we can understand now, when I am talking about number of molecules, how I can use stoichiometric coefficients for the calculation. Okay. Similarly, this ratio 1:3:2, this ratio can also mean number of moles. Alright, so it is not only the ratio of number of molecules, but we can also say that it is the ratio of number of moles. Right? Let's see. Again, I have 1:3:2 ratio. Alright, I have 1:3:2 ratio. This time I am saying, instead of molecules, I can interpret it as number of moles, ratio of number of moles. So this means that if I take 2 moles of nitrogen, okay, now we know the difference between number of molecules and number of moles of molecules. So now I do not have number of molecules of nitrogen as 2. I have number of moles of molecules of nitrogen as 2. Alright. So if I take 2 moles of nitrogen, this implies I would need 6 moles of hydrogen for complete reaction. And upon completing the reaction, these will form 4 moles of ammonia. Alright. I will get 4 moles of ammonia as my final product. Okay. So these number can also represent ratio of moles and not just ratio of number of molecules. Next, I said they might represent ratio of volume. Alright, ratio of volume. So this is true only in cases of gas. Alright, so here you have to remember that when I say this can represent ratio of, when I said that this can represent ratio of volume, you have to remember that it is true only when all the reactants and all the products, that is all the substances taking part in the reaction, are gaseous. Okay, so that is true only when all the substances taking part in the reaction are gaseous. They are not liquid or solid or aqueous or any other medium. Okay, so if all the substances, let's see here, in the reactants we have nitrogen. Nitrogen is a gas. Hydrogen is also a gas. The product which is going to be formed, ammonia, it is also a gaseous product. Alright, so in this case all the reactants are gaseous and even all the products are gaseous. So in this case I can say that, okay, in this case I can say that this ratio, the ratio represented by stoichiometric coefficient 1:3:2, this ratio is also the ratio of volumes of nitrogen, hydrogen and the product ammonia. Alright, that is, if I take 1 liter of nitrogen in a container, then for complete reaction I need 3 liters of hydrogen, and upon completing the reaction these gases will form 2 liter of ammonia as the product. Alright, similarly instead of liter it can be anything, say it can be milliliter, okay, or it can even be centimeter cube, it doesn't matter. Alright, and instead of 1 I can take again 2 centimeter cube or 2.5 centimeter cube of nitrogen or 3.6 centimeter cube of nitrogen, any random number. But correspondingly for a complete reaction, correspondingly I will also have to change, increase or decrease the volume of hydrogen taken. So for 2 centimeter cube, okay, for 2 centimeter cube I need to add 6 centimeter cube of hydrogen, and together they will form 4 centimeter cube of ammonia as the product. Alright, so this you have to remember, that this ratio can represent molecules, moles or volume ratio. Okay, now lastly I have written here mass ratio. Actually this is not true. Okay, I only wrote it because this is what confuses students. Okay, they all often assume that the ratio of stoichiometric coefficient, that is 1:3:2, also represents mass ratio. So that is not true. Alright. So if you find it written somewhere in a book, textbook, ignore that. Okay, it is wrong. This does not represent mass ratio. Okay. From the stoichiometric data, that is 1:3:2. So this stoichiometric data, okay, from the ratios of stoichiometric coefficients, I can calculate mass ratio, that is the ratio of masses which will take part in this reaction. But that ratio won't be equal to 1:3:2. Right? For example, let's review it quickly. Okay. See, here nitrogen is 1 mole. Okay, I can say that 1 mole of nitrogen reacts with 3 moles of hydrogen. So 1 mole of nitrogen weighs 28 gram. Okay, 3 moles of hydrogen, 1 mole of hydrogen weighs 2 gram. So 3 moles will weigh 6 gram. Okay, so 28 gram of nitrogen will react with 6 gram of hydrogen to form 1 mole of ammonia weighs 17 gram. So 2 moles will weigh 2 into 17, that is 34 gram. So using stoichiometric coefficient, I can calculate the mass ratio in which the reactants will react and in which the product will be formed. So nitrogen and hydrogen during formation of ammonia, okay, this is valid only for this specific reaction. Nitrogen and hydrogen might react in some other ratios, but the product formed will be different. Okay, but whenever they try to form ammonia, the ratio will be 1:3 and mass ratio will be 28 gram is to 6 gram is to 34 gram. Alright. Okay. So mass ratio comes out to be 14. Okay, 28 is to 6 is to 34. You can take 2 common. So 14 is to 3 is to 17. So nitrogen and hydrogen will always react in mass ratio of 14 is to 3 and the product will be formed in the ratio of, that is 14 is to 3 is to 17. So this represents mass ratio for this reaction. Okay, now again you can take 20 gram of nitrogen. Okay, in the container you can take 20 gram of nitrogen instead of 14 or 28. Okay, but correspondingly the mass of hydrogen also needs to be changed for a complete reaction, and the mass of the product formed ultimately will also correspondingly change. Okay, so stoichiometric coefficient can represent ratio of molecules, it can represent ratio of moles, and in cases of gaseous products and reactants it can represent ratio of volumes, but it does not represent ratio of mass. But we can calculate the mass ratio using stoichiometric coefficient. Okay, now once this is clear, let's move on to the calculation part. Okay, and let's solve some examples in which we have to use the stoichiometric data. Alright, so let's look at stoichiometric relation, that is between molecules, moles, volume and masses taking part in a reaction. Okay, see, for a balanced and complete chemical reaction such as AA plus BB gives CC plus DD. Okay, let's make it clear a bit. Here capital A and capital B are reactants. Alright, the letters capital A and capital B represents reactants, and the letters capital C and capital D, alright, the letters capital C and capital D represents products, and the small letters, that is small a, small b, small c and small d represents stoichiometric coefficient. So basically I have taken a hypothetical reaction. Okay, any hypothetical reaction. The number of reactants can be 2, less than 2, more than 2. Okay, doesn't matter. Similarly, number of products can be less than, greater than or equal to 2. Doesn't matter. Okay, it is a hypothetical reaction. Okay, capital letters represent reactants and products, and small letters represents their respective stoichiometric coefficient. So since I have already taken stoichiometric coefficients into account, it means I am talking about only a balanced chemical reaction. Okay, so what we are going to study is valid only for a balanced chemical reaction and a complete chemical reaction. A complete chemical reaction, I mean by this that the reaction has gone to completion, that is for complete consumption of reactants. The formula that we are going to study, the relation that we are going to study right now, will be valid only when the reactants completely take part in the reaction. There is no leftover material. Okay, so when at t is equal to 0, say at 0 seconds, you close the container with reactants only, and finally when you open the container after say a long time, by that the reaction has completed. So after a long time, when you open the container, there is no more A and B. Okay, there is no amount of A or B present in the container. We assume that only C and D is present. Okay, that is why I use the word for complete chemical reaction. That is a reaction which has gone to completion. That is complete consumption of reactants and complete formation of products. Okay, so for such a reaction, you have a relation. The relation is at moles of A reacted. Okay, that is, say A, I can take 1 mole, 2 mole, 3 mole. So moles of A reacted, let's say N1. N1 is the moles of A I took in the container, divided by small a, that is divided by stoichiometric coefficient of A, will always be equal to moles of B reacted. Let's say the moles of B I have taken in the container was N2, divided by small b will be equal to moles of C. Sorry, here instead of reacted it should be formed. Okay, moles of C formed. C and D are products, they are not reactants. So moles of D and C formed. So moles of C formed in the reaction divided by small c will be equal to moles of D formed in the reaction divided by small d. Okay, let's call this stoichiometric law. Okay, actually this law doesn't have a name. It's not really a law, it's a basic numerical problem. Okay, you can use unitary method to derive at this, to come up at this relation. Okay, but we are just studying it in form of formula because it will make your calculations much easier. Okay, unitary method can be a bit tacky to use in your questions, so that's why we are instead studying the formula. So let's say that N1 moles of A completely reacts with N2 moles of B to form N3 moles of C and N4 moles of D. Okay, so the relation says that N1 divided by small a, that is stoichiometric coefficient of A, will be equal to N2 divided by small b, that is stoichiometric coefficient of B, is equal to N3 divided by C is equal to N4 divided by D. Alright, so this relation is always valid as long as the reaction is balanced and there is complete consumption of reactants. Okay, so what is the use of this relation? The use of this relation is if you have any one of these quantities, that is N1, N2, N3, N4, if you know the data about any one component, any one reactant or any one of the products, even if you have 50 different reactants and products, but if you can calculate moles of any single one reactant or product, you can calculate moles of all the reactants and products. Okay, for example, let's say if I have the value for N2, that is moles of B I took initially in my container. Let's say moles of B initially taken by me were 4. Initially I took 4 moles of B for reaction. So once I know that, I can calculate how many moles of A was taken for complete reaction. What can I say? N1 divided by A is equal to 4 divided by B. So N1 is equal to A divided by B multiplied with 4. Okay, you already know small a small b by balancing. Okay, we have studied how to balance a chemical reaction in the last session. So once we can balance a chemical reaction, we will know the stoichiometric coefficient. That is, we know the value of small a, small b, small c and small d. Alright, we know these values. So basically we know A divided by B multiplied with 4 and we'll get the value of N1, that is moles of A required to react completely with 4 moles of B. Okay, and I can also calculate upon complete reaction what will happen. Initially I took 4 moles of B and N1 moles of A. Okay, so upon complete reaction A and B will be completely consumed. Okay, that is what we meant by complete reaction. So ultimately when I open my container, N1 will get converted to 0. That is no molecule or moles of A is left. Similarly, B left over will be 0 amount. So 0 moles. Instead of that, what I'll get in my container is N3 and N4, that is C and D. So I can also calculate value of N3. What will be value of N3? N3 will be C divided by B. Okay, I can calculate from here. From here I can calculate N3 is equal to, I can take C on the left hand side. So N3 is equal to C divided by B multiplied with 4. Similarly, I can calculate N4. What will be the value for N4? N4 will be D. Okay, N4 will be D divided by C multiplied with, divided by B. D divided by B multiplied with 4. Okay, so if I know moles of any one of the substances, I can calculate number of moles of any other substances. Okay, and once again, instead of moles of A reacted, moles of B reacted, moles of C formed and moles of D formed, instead of moles, here I can also use number of molecules. Okay, but if I have number of molecules of A reacted by small a, then here also I need to replace the moles by number of molecules, and again number of molecules here and number of molecules of D formed. Okay, and similarly, if all the reactants and products in the reaction are gaseous, then this I can also replace by volume. Okay, so volume of A reacted divided by small a is equal to volume of B reacted divided by small b is equal to volume of C formed divided by small c is equal to volume of D formed divided by small d. Again, this relation will be valid only for number of molecules, moles and volume. It will not be valid for mass. You cannot use this relation for mass. Okay, that is mass of A reacted divided by small a is not equal to mass of B reacted by small b. Okay, it is not valid for mass. Okay, what do we do if we have mass instead of moles? Well, let's see in the next session, and thanks for watching Edupedia.